So the agenda will be, we'll be discussing lecture 1, and then we have a class notebook and an assignment. I didn't get the time to go through the assignment yet. I'll be doing that tomorrow. So yeah, so the course, it starts with the basics of NLP, how things were done in the, some few years back up until 2012, when traditional NLP was used. And it was only after that, in 2013 or something, people started using neural networks and deep learning for NLP. I'm muting everyone for now. So if anyone wants to say something, please unmute yourself. And yeah, thanks. Yeah, so this course is about, we'll be like starting with the basics of NLP. And then in the further lectures, we'll be covering more advanced methods. And like the first lecture also covers how human language is very complicated. It got nothing to do with machines or computers, just the human language itself is pretty complicated. And then we try to understand how to enable machines to understand human language, which is called natural language understanding. And then the course has some assignments and also projects on topics like building named entity recognitions, word meanings, question answering systems, etc. So this is a practical course, the instructor says. So it sure looks like that, and we have so many things to do. So CS224n has been there for many years now. Like a couple of days ago, I even came across videos from 2012. I didn't go through them, but there were like 100 videos in a playlist, and each was around some 15 to 20 minutes or something. Yeah. So this year's course has 3 guest lectures, which covers some advanced topics, and it has 5 assignments. And the assignments are on topics like neural machine translation and subword modeling. And also for this course, this year, they have switched to PyTorch from TensorFlow. So coming to the assignments, we hear Christopher Manning say in the lecture that collaboration is allowed, but do not copy the code from GitHub. So maybe we can also try and do that. I mean, not to copy the code from GitHub, so that that way we can get the most out of this course. The first 2 assignments are based on Python. They got nothing to do with PyTorch, so there is no deep learning library required for the first 2 assignments. There is also 1 lecture on Python review. The video is not available for that, but the slides are there. And assignments 3, 4, and 5 will be on PyTorch. But as discussed in the previous session, if depending on the interest of ours, we can also give it a try in TensorFlow. So this course has a final project, a default final project or a custom project. So the default project is to work on question answering using the squad dataset. There are also some project ideas which we can find here. We'll go through that. Can you all see the project ideas screen?
Yep.
Okay, so these are some of the project ideas that like character-based word vectors, multi-hop question answering in the wild, yeah, improving NLP representation learning with definitions. So we can go through these and also some of the other projects. So it's still too early to think of projects, but yeah, I think having a specific project in mind will help us. Yeah, so you must have seen this cartoon on the right from the lecture slides or during the lecture. Uh, so this is just one example where, I mean, we all find language and communication so easy and intuitive, but there are a lot of complications. Languages are human created systems which are adaptable, and like there are so many languages all throughout the world. So we use languages for representing maths, for writing fictional stories, for talking to people. And yeah, so if you have gone through this cartoon here, yeah, so this part here says every choice of phrases and spelling and tone and timing carries countless signals and context and subtext and more. So yeah, there are a lot of things that one has to consider when we are working on language, especially when we want to enable machines to understand these human languages. So which is not that easy. So, like the knowledge and intelligence is attained by us humans with the help of language. So, to build models which are intelligent enough, especially at the level of artificial intelligence or AGI, we need machines to understand languages as well. And comparatively with computer vision, I mean, vision in general, language is pretty recent. Like there are creatures uh, which have the ability to see from many thousands of years, whereas language is much more recent comparatively. And even when it comes to machines, computer vision has seen a lot of progress over the few years, which is much more than NLP. But thanks to some of the progress that has happened in the past couple of years, NLP too is catching up. So these are all some of so just going through some of the links to learn about language and language evolution has led me to some very interesting articles and all. So it just maybe like making machines to communicate and understand with other machines seems to be an easier problem to solve than enabling them to understand human languages. So it's just a thought that crossed my mind when I was going through some of the articles on languages and how the language has evolved. So before we can think about enabling machines to understand human languages and sentences or conversations, we have to start with words. Words are the basic building blocks of languages, any language. And when we are talking about words, we can't separate or leave out meanings. So if it exists, then it has a meaning. So philosophically, maybe yes, but linguistically, that's not always true. So when we come across a word which we never heard of, the first thing we do is we search for it. We try to know what it is. So if there's a word which doesn't relate to something, then it's like there's not much use with it. So meanings are the ideas which are represented by the words or the phrases or the any forms of in any form or parts of languages or communication. And they are very essential for the languages. So for us humans, we can learn meanings either from our experiences or from the way we learn and adapt. And we also have these physical dictionaries which have like thousands and thousands of words and their meanings. So how do we get the machines do that? So we have something like WordNet, which is kind of a software which gives informations about words, their synonyms and hypernyms. So as we can see here, this image on the right, it gives us the synonym sets for the word good. So as per this framework, or as per WordNet, good can be in different kind of synonym sets. These are called syn sets, which are synonym sets. So though it is providing some sort of information, it is not really that good, because there will be some situations where WordNet doesn't do that good. And though it provides some meanings and also can help in grouping together similar words, it doesn't scale well, because WordNet is created, it is updated and adapted for the new words that keep coming up manually with the help of human labor, which is not just feasible considering the countless number of words that we have in any language. So that is why there is a need to have another representation or framework for words, which is very scalable and robust to use. So how can we represent words? So when we are working with images or computer vision, what we do is we capture the image and we convert that probably into an array. An array, again, is nothing but a matrix or list of numbers. So be it text or images or speech, before really taking that up and feeding that to a model or a program or an algorithm, it has to be converted into some sort of numerical form. So how can we do that for words? One way of doing that is using one-hot encoding, which most of you must be already familiar with. So this is one example here, the hotel motel example, which is one-hot encoding representation. The way this works is if you have vocabulary V with n words. So when I say vocabulary, it is nothing but the list of all unique words that we have in a text. So if we have like 15 words, let's say, in our vocabulary, and those are the only words that we are going to use, what we can do is we can maybe put them in some sort of order and assign number 1 to the position in which they belong to. So here, if you see, motel has one probably at 15, 14, 11th index, whereas hotel has it at around 8. So this way, what we are able to achieve is that for every word, we have unique representation, which is good. But then the problem here is that if in real time, the number of words won't be 15 or 10 or hundreds. They will probably be in thousands and much, much more. So in that case, having one-hot encoding representation like this is going to kill a lot of space. It needs a lot of space, and we can see these are nothing but sparse vectors, which are not that good. So just think about having this kind of representation for all the words that we have in an English dictionary, like probably more than 150K words that we have in a dictionary. So we'll be using so much space, and the amount of information it conveys is very, very little. So, but yes, this works in giving unique representation to words, but we might as well just assign something random to every word. Even that works. So that's why, I mean, when something works, it doesn't mean it is necessarily efficient. So we need some other kind of representation of words, which not only gives unique representation for every word, but it also somehow manages to contain some sort of semantic and similarity information between different words. So what we just discussed right now is called localist representation, the one-hot encoding. We can go, the next step or the further improvement in this is distributed representation. What we need is, we need some sort of representation which will give us the features of both one-hot encoding and WordNet. So as I said, one-hot encoding gives us unique representation for every word. And on the other hand, WordNet gives us some sort of synonyms, which by that it helps us in knowing words which are similar to each other. So somehow we have to combine these two, and we need to have a better representation of words. And that can be done using distributed representation. As we can see here, there is one example for the word banking, which here is represented by a vector of uh, 9 dimensions. So unlike one-hot encoding where most of the values are zeros and only one index has a value 1, here we have a distributed representation for the word banking. So how do we get that? It's something that we will see later.
Hey, just so you know, I think we lost you. Not sure if anybody can hear me.
Yeah, I can hear you.
Hey guys, can anybody hear me now?
Yeah.
Yeah.
Okay, good deal. I was saying while we're waiting for the host to try to get reconnected, does anybody have any questions on like the different types of representation or anything we've gone over so far?
Yeah, I just posted one question.
There were a few questions, like if you scroll up. Yeah.
Okay. So let's start with the negative value. So the idea, right, is like the naive way that we represent words, or the way that we turn them into numbers, is we just give every word basically a different number, right? So we can keep track of different words. But the problem with that is that what we really want is we want to kind of get at the meaning behind the words. And so we don't want to just represent them naively as like, you know, water is 1, fire is 2, that kind of thing. We want there to be some meaning, like geometrically, between them. And so what the idea in the vectors is to embed them into some n-dimensional space where similar words should be close to each other, like geometrically. And so the negative value doesn't really signify anything. It's just it's like the categorical embeddings that FastAI uses. It's just saying that we're projecting all these words into a new dimensional space. And so the idea being, like, let's say we have the words banking and finance, and you're representing them across 2 dimensions, you would expect that the numbers are pretty close to each other. Does that make sense? It's kind of a weird concept, I think.
Yeah, Daniel, it does make sense. I might add one more thing, that it's negative because we are spanning over an range which goes from negative to whole positive. Suppose if you are just limiting ourselves to just positive values, then there will be no negative values. So in absolute terms, negative values don't have any meaning. But the closeness of those values for different vector representation of specific words, the different the closeness of those values for different representations of different words do have value. Like as you were saying, banking and finance, they might be having very close vector representations, which might tell them that they are very much connected.
Yeah, and I think the key thing is that you're not restricted to like 4 your dimensions. I've seen kind of a couple different ways of doing it, and one is to say that they can have a value between 0 and 1, and another is they can have a value between like -1 and +1. But it could be any range that you wanted.
Exactly. So wherever, it's negative doesn't mean that it has some special meaning of net negative. So if you are limiting ourselves to just 0 and 1, just suppose we take that case. So the science does not mean anything there. It's just the relative distances between them, right?
Yeah, exactly. So like water and fire, if there was some dimension that represented something related to it, you would expect maybe 1 to be +1 and 1 to be -1 or something like that.
Exactly. And if you are limiting ourselves between like 0 and 1, that one might be 0, another might be just 1.
Yeah, exactly. Just like, and typically when you're embedding stuff into a dimensional space, because language is so complicated that it'll be, you know, like somewhere around 300 dimensions is what I've seen typically.
So like I had one question, like why, I think Srinivas anyway answered it. So why we are using different U and V vectors for when the word is at the center when word is at the neighborhood. So that was my question. One was for U and U is for when word is at the center, and I think V is when it's in the neighborhood. Why we have two different uh, things from SVD.
Yeah. The high level for the word2vec algorithm is that there's basically two sub algorithms. Like what we're doing is we're trying to figure out how to embed words or word tokens into some dimensional space. And so one algorithm says, all right, here's how we're going to learn this. We're going to take, let's say, 5 words in a sentence, and we're going to try to predict the word in the middle using the context words around it. And I forget if that's skipgram or if it's the other way around, but that's one way. And then the other way is to try to predict the surrounding words given the word in the middle. I think something like that.
Yeah, exactly. That's you're correct. So in the second case, we are using V as the, if I'm not wrong, we are using V, and the first case we are using U as the, what do you call, for calculating the probabilities. So my question was like, why we are using the two different things. I might not have reached that stage somewhere. I think it's maybe in the second lecture, the answer.
Yeah, I think he covers it in the second lecture. It's mainly to do with propagation.
Can you come again?
When we separate the U into V transpose, whereas if U and V happen to be the same, he mentions it'll end up as a U squared. So he was saying there was an issue with the back propagation, so it's just like a mathematical thing, to just make that simple. And the other explanation he gives is, if you think about it, it's pretty much the same, because the moment your context, if you have your center word and you're looking at a context word to the left, and if you move one right, now that context word becomes your center word. So, it keeps changing in a very similar fashion throughout.
So, like, is it just because of the mathematical convenience, as you mentioned?
Yes.
Okay, I'll finish the part like lecture 2 and maybe like
and like Srinivas mentioned, that at the end of the day, you're actually just end up averaging both of them.
All right, and it looks like Avinash is back. If you want to share your screen again and keep going, that'd be awesome. Oh, maybe I'm wrong. Hang on one sec.
While we're waiting, a quick question. What does it mean to add dimensions? I mean, that's just, I think what that means is how many elements are in the vector, but what is it actually doing?
Yeah, good question. So the best way I think to understand it is with like topic models. And so the way they work is they have this idea that you can represent any, let's say paragraph of text as some percentage of different topics, right? So like, let's say it's news articles and there's like sports and there's politics and stuff like that. So the idea is that every dimension, or you could think like every kind of column in a spreadsheet or an array or whatever, represents a different dimension that means something. So politics, sports, whatever. The idea here with like word2vec is that we're choosing some number of dimensions, and then it's going to learn different, let's say, concepts. And we won't have like an exact definition of them. It's just going to kind of cluster similar things together. And so all it means is you choose kind of arbitrarily, or maybe data-driven way, like how many possible dimensions there are to describe something on. And so if you have a lot of variation, a lot of different things, then you need more dimensions to be able to describe different things.
And we don't really, this is kind of similar to CNNs and image recognition, because we don't necessarily know what the dimensions are that the machines are finding.
Well, we can choose in like word2vec, we can choose how many, like, how many dimensions it's allowed to compress things. So think about it this way. Think about, like, we have this huge, very, sparse vector, right? And we're compressing it into a smaller matrix, basically, or a smaller vector. And so the smaller vector, we choose how many dimensions we want by saying, here's the maximum length, or here's the length of the vector.
Right. So, but we don't. Yeah. Go on. Go ahead.
So imagine that your vocabulary is 100,000 different word tokens, and your dimensions in Word2Vec are, 20. It's going to take the task of trying to predict the surrounding words or the center word or whatever, but the input that it gets to make those predictions is that embedding layer of, let's say, 10 dimensions or something like that. And so it has to learn the best representation it can in that embedding layer, and we can choose the size of the embedding layer.
I don't know if anybody else welcome to jump in. I didn't get that last part. In other words, when we say these dimensions, this is very different from the sort of window size of the surrounding words. Is that correct?
Yeah, that's exactly right. So think about it this way. Like, think about it like a feed-forward neural network, where the first, like, the inputs are a vector that's the size of your vocabulary, or the length of your vocabulary, right?
Yeah.
And then the next layer is, let's say, a smaller, like, let's say you only have 10 hidden units or something like that. That would be the number of dimensions that you have, because it takes those 100,000 inputs and it compresses it down to 10 inputs to the next layer.
Mm-hmm.
And so the window.
Okay. Yep. Go ahead.
The window size is how big of a context you'll give it to make those predictions. But every word is getting compressed from, like, let's say 100,000 length vector into, let's say, a 300 length vector. Mm-hmm. And so because that's the input, and then you have kind of gradient descent teaching it, it learns a compact and efficient representation.
Right, that all makes sense. Can we take a quick example? So since the World Cup is going on, this Megan Rapinoe. So if we see an article about her, we could well say, well, it's #1 sports. Then you could say it's maybe politics because she's tweeting at Trump or whatever. Then you could say, it may be about fashion. It may be about, in other words, you could start to, because she's wearing a uniform or whatever. I'm just making stuff up, right? It could be about endurance. It could be about who knows what. Those are the dimensions. And what I'm asking really is, I'm making these things up, but the machine is just running number algorithms, and we don't really know what it's doing. It doesn't necessarily correspond to anything that we can conceive of until we sort of look at it in that vector space and go, oh, well, it's near that word, and it's near that word, and it's near that word. We can kind of then say, well, that seems to be the connections. Those are sort of the dimensions it seems to have chosen. Is that right?
That's exactly right. That's exactly right.
Oh, very cool.
And I think that's why they. Oh, go ahead.
Yeah, sorry. Well, I was going to say, it could be coming up with stuff that we don't think of. And in fact, it probably is, because in the examples I've seen of Word2Vec, you can see all sorts of things that make a lot of sense. And then one will jump out and you kind of go, what is that doing in there?
Yeah, definitely.
Yeah.
And I think that's a space where the NLP community is really evolving around, and we'll learn about this as we keep going, but with, like, contextualized word embeddings, we start to get to stuff where it's like the same word gets embedded into a different dimensional space depending on the surrounding context. And I think that's to solve problems like you just described.
Great, thanks so much for that.
Daniel, you were saying that it moves from like 10,000 dimensional space to a 300 dimensional space. So where is this initial 10,000 dimensional space coming from? How do we know what is the size of that dimension? Is it the total number of words? It's a sparse matrix of total number of words were hot encoded, and then we are compressing it into lower dimensional space. Is it something like that?
That's exactly it. So like the way you would kind of start, right, is you take whatever your documents are, if they're tweets, if they're legal contracts, any source of text, you would take all your documents, and the first thing you do is you'd iterate through all of them, and you'd say, like, let me make a list, an empty list that'll contain the unique words. And as I go through the documents, every time I find a word I haven't seen before, let me add it to the list. And so you get every unique word in your set of documents. And then you go through and you say, okay, now let's make them, lowercase so that I don't have a difference between that. Let me maybe chop off things like ing or different stuff like that. And then I'll get the number of unique, let's call it like word tokens, right? And then you have a mapping where you have this list, and at like index 0, let's say you have king, and index 1 you have man, index 2 you have woman, etc. And that's where your initial vector comes from. Is basically just a dictionary that maps from the word to a number.
So the dimension of the initial, the sparse matrix will be equal to number of unique words. Am I correct here?
That's exactly right. That's exactly right. And where you run into some interesting situations, and I think this is like a little different from most of machine learning, is that I think it can be kind of common if you just train your model on like your set of documents. It would be easy, I think, to run into a word that you've never seen before in the future. And so what will happen there is it just won't map to a value and it gets ignored. And there's a bunch of other strategies. There's some really cool stuff like Facebook's done where they embed words using the characters, like individual things. Or we take these huge, pre-trained word2vec things from Google where they've, done it on this huge web crawl where they've seen billions of unique, word tokens. But fundamentally, it starts with a dictionary that maps from a word to a number, and every word has a unique number or a unique position in an array or a vector. And then you're learning a model that takes that word and embeds it into that semantic dimensional space.
So maybe I'm like going a bit further, or maybe it's mentioned further in the lecture, but won't it be better if we like use the previously trained embeddings, like those embeddings which are available in the form of models? I'm not sure whether it is the case or something.
Yeah, 100%. That's, I think, where a lot of advancements have come from, is rather than trying to take like a small set of documents or tweets that we have, the better approach, and you see this kind of with like ULM fit and stuff like that, is you start with a pre-trained, model. So this could be Stanford's like Glove or Word2Vec or something like that. And then you either just use that how it is, or you fine tune it, on your corpus or your set of documents.
Cool, man. Thanks.
Can you talk a little bit about fine tuning? What that means?
Yeah. So let's say that we have the model architecture, like the code for it, and the weights. Or let's say Google has said, okay, we're going to crawl the web and we're going to take 1 billion web pages from, Wikipedia and Reddit and everywhere. And then we're going to run this Word2Vec algorithm on that, entire huge set of documents. And when they do that, because it's such a diverse and large set of data, they learn really good representations. And so they don't typically do this, but if they did make the whole model available, right? So the weights, the code architecture, all that, then what you could do is you could, just like with, fine tuning a CNN off of ImageNet, something that was already trained on ImageNet, we could take that same model and then say, here, we're going to plug some new data into it from our corpus, and we're going to run it through that.
And if we did that, if our corpus was kind of tiny, say, I mean, I don't know, it's a book or a play or some small amount of words, how would that not become trivial and sort of, what I mean, have no bearing on the numbers that came out?
Yeah, well, then you get into some kind of interesting issues, like you're saying, like they call it catastrophic forgetting, right? Where it focuses so much on like a small set of training data that it forgets all the useful things it's learned from the diverse data set. And so I think you have to be careful about stuff like that.
Mm-hmm. So that's where you play around with it and see what seems to be working.
Yeah, exactly. And in practice, I think for stuff like Glove or Word2Vec, you typically just take it how it is. The fine-tuning thing has been more around like language models, like BERT and Elmo, and that's, I think, all stuff we get to in the fifth lesson. But I think for me, the important thing to take away from this lesson is that if we just we have to encode words into numbers so that we can use machine learning on those numbers, and the best way to do that is to compress these really long, sparse arrays into like dense, semantically meaningful, smaller vectors with similar words or similar meanings being in similar places.
Yep.
What else?
And is there a way?
No, go ahead.
Sorry.
Go ahead.
Yeah, I don't mean to sort of jump ahead, but I'll just toss this out there. I was looking at one of the Kaggle competitions where they're trying to, well, it doesn't really matter what, but let's just say it's an IMDb, data set having to do with rating things. And if you say, this wasn't at all terrible, you're kind of having it's a weird way of saying this was good, but it would be interesting to be able to feed in somehow that fact, right? That even though you've got the word terrible in there, it's kind of the negation of it that we're interested in. And I don't know, maybe the network finds that by itself, but is that another kind of tuning, or does that just become feature engineering?
That's such a great question. And that's something that the NLP community, I think, really struggled with until they came out with recurrent neural networks. Because what we're talking about is kind of two different things. One is we want to embed the word not or negative or not so much, or different things like that. We'd want to embed it into some dimensional space that conveys like a negation of whatever's about to come next. And then we'd also want to embed words like bad, evil, terrible, horrible into a similar like space. But those are, if we do that, right, all we've done is we have a good representation of the individual words. And so one way to solve that is to embed words like not individually, right? To embed them like two at a time, for example. But another way to solve it is to use a recurrent neural network for whatever your modeling task is. So the canonical example is like we're trying to predict sentiment around like movie reviews or something like that. And if you have a good representation, then you can train a recurrent model where it sees things in sequences or in steps. And so the first token that it sees is like, the, and then movie, was, not, terrible. And it learns that when it finds a token that represents negation, and which is then followed by a token that represents, bad or something like that, it knows that that actually means like a positive sentiment or something like that.
Like a negative times a negative is a positive.
Yeah, exactly. and all that depends on like the task that you're doing and what your data looks like. And so, you know, you have stuff like sarcasm and all those different things. And I think that more sophisticated or complex neural network architectures for the downstream task, like for whatever the thing you really care about is, they sort of solve that well if you have a good representation of the meaning of the individual words, or at least that's my take on it.
Really interesting.
So what else kind of jumped out to everybody in the first lecture? And feel free to type in the chat or whatever.
Did anyone work on the homework or that? I'm just curious how hard they are or how much time they take.
I looked at it a little bit. I didn't actually go through and do any of them. They seem like pretty reasonable. And I think maybe something to decide like individually is how you like to learn. So for me, I like to have some sort of project and then try to apply what I'm learning to the project. And other people like to say like, okay, what's the best way to do this? Let me go through the kind of structured homework. And I think there's value in different approaches. So I think we'll have to kind of figure out individually and as a group, like how to best take the theoretical stuff we're learning and apply it. Because like, it's really unlikely that any of us are going to be training our own word-to-vec, models. Most likely we'll be using ones that other people made. But I think it's important to know how they work. So like for me, what I would want to get out of this lesson is how do I use like Stanford's GLOVE model or Google's Word2Vec and embed something into a dimensional space? Or how do I use a library like GenSim to use that stuff? Or how do I keep track of, my input text and then turning it into a dictionary, that then goes into that model? So it depends what you want to get out of it too, I think. But the homeworks look decently challenging, I think. But I don't know if they're totally aligned with, like for me, what I want to get out of the course, if that makes sense.
I think my take on the first part of the assignment is that it's pretty easy. It's pretty much just creating your own vocabulary and then creating that co-occurrence matrix, so simple Python code. And then answering to your question about the takeaways, I think how simple this model is, and it still seems to work pretty good. And like kind of to look at the drawbacks, those are kind of the main takeaways, I think, from this lesson for me.
Yeah, it's amazing just throwing a lot of data and computed something, like how good the embeddings end up being.
All right.
I have what you were saying about the kinds of things you'd like to get out. That's exactly the kind of thing I'd like to get out of this. So I guess that means, it'd be nice to find a way to, I don't know, sort of agree on tasks that a number of people want to do, like, I don't know. Yeah, I guess that's still an open question. And maybe it's just individual.
Yeah, we could start a thread maybe around like different project ideas that relate to the lessons. Like, there's tons of good stuff in the homeworks, and it's good to go through them. And I think it depends on your individual like level of motivation. But yeah, maybe we can start a thread around different ideas of projects that people find interesting or would want to collaborate on, and that would give us an outlet for the more theoretical stuff we're learning.
Yeah, I would especially be interested in the collaboration part, because I don't know about anybody else, but I'm kind of isolated out in New Hampshire. you know, picture woods and nothing. Well, that's not quite true. But, and so, you know, the chance to connect with someone else on sort of thinking about this stuff is very valuable, you know, as is just this meetup.
Yeah, I know just what you mean, man. I feel the same way.
I think we should have a like maybe one meeting, or maybe like we can dedicate some 10-15 minutes of a meeting but in the middle of the course for discussing other various project ideas. So maybe 2 or 3 people are thinking on the same lines. We can just connect and collaborate.
Yeah, that's a great idea. Well, I think we're coming up on 2 o'clock. Anything else you guys wanted to cover before we call it a day?
I have a query. Like, what will be our agenda for next meeting? Will we be trying to go through the first lecture itself, or we'll do like some abridged version of first lecture and maybe jump to lecture 2 directly?
Yeah, that's a good question. I would look to the wisdom of the crowd a little bit. I think it would be good to see code. I think that always helps. This lecture we were just going over theory, but I think seeing code is useful. So whether that comes from the homework or us coming up with different examples, I think that would I don't know. My intuition is that would help.
Yeah, I agree.
Okay, maybe let's discuss in Slack and let's see what people say about maybe like next meeting if they want. This discussion, I mean the chapter 1 itself again discussed, or maybe like lecture 1 or lecture 2.
Yeah, I think that's a good idea. And this course too, from looking at it, I think it starts out like not too bad, but it gets very complicated pretty quickly. So I would err on the side of going too slowly, and you know, leave no one behind, than trying to rush through it.
Yeah, completely agree.
Yeah, I have one other suggestion. You know, when I look at the math notation, I am often trying to figure out exactly what it's saying. I sometimes know, and I don't know. That would be a helpful thing at some point to go through just sort of in plain English. What is this saying? You know, from I equals 0 to the number of cases, we're doing this, this, and this. And
Yeah,
like
I agree.
in some of the math, it has like sum of something, and then right next to it, sum of something else. And I'm going, what is it doing? Is it multiplying those two things together, or what? That kind of thing.
Yeah.
Yeah,
So
David.
Let's plan maybe for next week. Anybody that hasn't had a chance, try to go through the first 2 video lectures, or at least the slides, and at least look at the code, the preview. And we'll work on getting some example code for the lecture that says, you know, word vectors 2 and word senses, and maybe we can work on trying to convert some of the more complicated math formulas, you know, into code or into something a little bit more digestible.
Yeah, that sounds great.
Yeah, and I shared a PDF. This is from Jeremy Howard. I find it quite useful. It's a kind of an explanation of all the linear algebra and math you need for deep learning. He and Terence Howard have done a pretty good job. So I shared the PDF link, but I know there used to be a web page too, but I just can't find it right now.
Is that the link in the chat?
I think
Yeah.
I'll find and try to post that in Slack. Yeah.
Okay, I got it.
Oh,
Yeah, it's
okay,
like
great.
explain.ai and yeah.
The other, I think, really useful resource, because the first 2 lectures are all about Word2Vec and then Glove, and there's this really, really good blog post called The Illustrated Word2Vec, and some of you guys are probably familiar with. It's got a really nice visual explanation of kind of what's going on. And so I'd recommend everybody, find 15, 20 minutes or so to go through that and get a sense of it. All right. Well, I guess I will talk to you guys next week. Everybody have a good week and see you then.
Thanks so much. Take care.